Welcome, estudiantes, to the lesson on 6.10. We're going to talk about functions and their graphs, specifically focusing our attention on linear graphs, quadratic graphs and functions, and exponential functions and graphs. So make sure you know these words and phrases by the end of this lesson. Make sure you are familiar with those and using the extra examples in the book, of which there are 12 in this lesson. So you've got a lot of extra examples in the book. I'm not going to do anywhere near that many here, but I'm going to try to hit the major points that you should know as best as I can. And so let's get started with a couple of definitions. First of all, so a function, we'll need to know what that is, but before we even talk about functions, we need to talk about what a relation is. So a relation, kind of like you're related to somebody, there's a relationship between the two of you. It's any set of ordered pairs. So you could have like 1, 2, 2, 4, something like that. You could have that set of ordered pairs. You could have a collection of those, but it doesn't really make a difference. You could have something like this. Don't write this down for me, but you could have 1, 2, and 1, 3, and 1, 4, and you could have 2, 6, and 3, -5, something like that. That would be a relation if we took all those together. That's a set of ordered pairs right there. A function, however, is slightly different. There's a catch to a function, and there's a little bit extra. So it's still a relation. So it's a set of ordered pairs. A function is a relation where each x value, which sometimes they're not labeled x and y, so it would be the first value or the independent variable in an ordered pair. The independent variable, the one that is kind of stands alone, these are our first values we're getting, matches up with a unique, that's really critical right there, unique. It's a unique y value. Or sometimes they're not y's, sometimes they're just the second number or second thing in the ordered pair. These are the dependent variables. And so over here, this would be a relation but not a function, because you have these x values of 1, 1, and 1. They should all match up with the same y value, but they don't. They don't have this unique y value. So if I got rid of this one and this one, now I would have a function. I have different x values here, and they match up with unique y values here. We'll talk a little bit more about what makes a function in terms of their graphs in our next example. So let's check that out. Example 1 here. You'll notice I have a vertical line right here. Hint, hint about what we're doing here. You may have seen something like this before, especially if you've taken algebra. You should recognize this phrase right here, the vertical line test. So use the vertical line test to determine which graphs represent functions. And then let's circle this part here, use our different color for that. Vertical line test is just this. It's any, or how we implement the test, we take any vertical line, so any vertical line on the graph. I'm going to double underline any, because that's really critical. Any vertical line. It's not just a single vertical line, but any one that you put on there can only cross through one point. And so I'm going to make, these can just be sketches, they don't have to be to scale drawings here, but I'm going to make 6 different small graphs here, and so just follow along with me as I do that. And you'll need to do the same thing on your page. So 6 small graphs, I'm going to put arrows at the end of each one because these go on forever and ever. I'll just go 4 in each direction. If you have graph paper, you'll notice this set of notes was kind of on graph paper or on a graph slide, you could say. And so if you're using graph paper, that's a really good idea. If not, though, you'll be okay without it. These ones don't need to be drawn to scale. So let's draw 6 small graphs. And I think, yeah, I'm going to cheat. I am just going to take the graphs I drew here and copy and paste them to make my 6. So if you need to pause the video, go ahead and feel free to do that if you need to catch up with me. But I'm going to just take these, copy, or duplicate, that's even better. Oh, I lost my arrows, some of them, but I'll just have to include those quickly. Okay, so that's your axes, and then I'm going to use a thinner line to represent the graphs that I'm actually drawing. These don't need to be drawn to scale in any particular place, just basically in the same spot where I'm putting them. So let's just draw any old line. I'm going to say the Xintercept or the Yintercept. It looks like it's 1 and -1-ish, but it doesn't really make a difference. Just draw any old line. For this next one, I'm going to use my freehand sketch tool. Should be okay. And I'm just going to draw any old parabola. So a real parabola wouldn't be quite, I think it'd be a little less drastic right there, but you get the idea there. A parabola, we've got this U shape. So this one over here is a line, parabola. Oh, hold on. I meant to draw a different one. The line was fine. I'm getting ahead of myself though. I actually wanted to draw more of an S shape here. There we go. And then a parabola I meant to do here, but I'm going to make it a kind of a sideways parabola. Like that. And then over here, closed circle there, open circle here. Closed circle, open circle. That pattern is going to continue. Closed circle, open circle, closed circle, open circle, closed and open, and then connect the closed and open circles horizontally together, like you see here. And then we'll do the same thing, the same sort of thing, but use closed circles in both spots, like this. And then for this last one, something called a hyperbola. Maybe you remember that. We're trying to draw that general shape. So it's like it's almost like a parabola, but there's 2 of them. A little bit too much. I'm trying to use these lines here and here as the lines that they get really close to, but never actually touch. Like that. So these are just sketches. But now we're going to try the vertical line test. So we're going to take, oops, there should be a little line there, okay. We're going to take this vertical line, I'm going to move it around, and we're going to see. So this represents any vertical line. As I move along the graph, it only can touch at one point. So here, this one, as I move along, it's all good. It only touches at one point everywhere I go. So this one is good to go. I'll get this ready for the next one. This would be a yes right here. So let's put that as our answer here. Is this one a function? Yes, because every x value matches up with one and only one y value. As we move the vertical line along the graph here, it looks like we're good, It gets kind of close there, but nope, we're still good. And as we move along, we're still going to be good, The vertical line will just touch one point as we move along there. So here is another yes. This is another one that is a function. It passes the vertical line test. Let's keep that idea going. So here, it's good. Up to here, it's not even touching any points. That's fine. But here it touches just one, but then all of a sudden, boom, uh-oh. So we got a problem here. It touches 2 points. So I have an x value. For instance, I can say I have an x value of 1 that matches up with 2 different y values, and that's no good. If we have a function, that can't happen. So let's take our different color and draw in. Let's make it dashed just because I feel like it could be solid, but I'm going to make it dashed. So here's an example of a vertical line that crosses in 2 different points. Let's circle that point right there and circle that point right there. That's no good. So this one we're going to say no, it doesn't pass the vertical line test, because I can draw a vertical line on that graph that crosses through 2 points on the graph, 2 or more points. So I move along down here now. Looks like this is good, and then, uh-oh, what happens here? What about that point? Or what about this one? Similarly, this one and this one. What about these? Well, if it's a closed circle, that means that's included, but if it's open, that means that's not included right there. Just like on a 2-dimensional linear graph, this is a Cartesian plane. So if we had just the number line, basically, if we had that, we had open circles, and we said like x is greater than or equal to 7, stuff like that. We do the same sorts of things on graphs here. So here, does it actually cross 2 points? No, it's crossing 1 point here. But even though it kind of looks like it does here, that's an open circle, meaning there's not actually a point right there. And so as I move along here, this one is all good. However, this one over here, I do run into a problem. So it's all good here, 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 still good, still good. And then all of a sudden, boom, right there, I'm crossing 2 points at once. Even though that only happens right there and right there, because it happens once or more, it's not a function. So on this one, we're going to draw nothing here, because this one passes. This one was good, so this one's a yes. But this one, let's draw our vertical line. Right here is an example of a vertical line that actually crosses. Why don't we make these solid? Let's do that. I can do that. That's fine. The different color makes it stand out. That's what I was mostly worried about, is that you'd think it was part of the graph itself, but it's not. It's just a vertical line test for that. So this would be a no, because we found a line. We found 1 or more lines. There's actually 2 here that would make it not work, but we found 1 or more lines that don't work with the vertical line test. And then as I go over here with this one, from here right there, the tangent point here to the tangent point there, those values are good, but then if I go past that to the left or to the right, no good anymore, no good over here. So let's draw, using our different color here, let's draw a vertical line. We'll make it here. Oops, different color. Red, there you are. One of my favorite bands right there, Red. Should check them out. They're really good. But this is a no, because it crosses more than 1 point. We found a vertical line where that happens. Let's move on to just a summary here. Summary of functions and graphs. This isn't going to be all the possible functions and graphs that there are. So I'm going to say it's a summary of, why don't I put that up here? I'll have you put that up here. Some functions and graphs. This is not all of them. This is just some of them. We'll put the type here. We'll put the general form in this row, and we'll put the general graph in this last slot for each one. So general form, general graph, and the type. We're just going to be talking about linear, quadratic, and exponential with this lesson. There's a lot more. You could do cubic, you could do quartic, is actually to the 4th power, the 4th degree. You could do absolute value. We've got exponential here. You could do absolute value. You could do, oh, what else am I thinking? Like a ceiling function or a floor function. You might have never heard of that. I don't know. But you could do all kinds of different functions here. These are just the general. I hesitate to say big 3 because cubic's pretty important. I think absolute value is pretty important too. They get used a lot. But these are definitely 3 of the big ones that you'll see. So this one, the general form, is y equals ax plus b. Something times x plus some other number. And then let's make a little note here that this is the same as, you may see this notation instead. So if you see f of x equals something x and something else, don't get freaked out, or don't freak out. It's okay. It's the same as y. So you could see that in these other ones as well. You could see f of x instead of y. That's okay. So here, y equals ax squared plus bx plus c. That's the general form. But you can't have a 0 value for a right here. So let's make a little note of that here too. Otherwise, the x squared part drops out and it becomes linear instead of quadratic. So you cannot have a equal to 0. So a does not equal 0. And in this one, y equals a to the x power, exponential. So this is where this has to also be true at the same time. A has to be greater than 0. No negative values for a, and no 0 values either. And a cannot equal 1, because then you just have the number itself. That wouldn't be very interesting at all. So we have this. Let's make our general graph. So let's draw a set of axes. I'll use what I had been doing here. I want to use a thicker line for my axes. A set of axes here. This is just the general graph, so this can be just a quick sketch. Doesn't need to be real pretty. And I think I'm going to cheat again. I'm going to take this and just duplicate it 3 times. And you do the same though. So just take that and do that over here and over here as well. Pause if you need to. I'm going to hand sketch these ones here. It doesn't have to go any particular place. I'm trying to not make it go through the origin so you don't, wow, so you don't think it has to go through the origin. There we go. That's more what I'm looking for. So just any old line. So this is the graph of a, or we call this a line. So let's put that in a different color. This is a line right here. This one is going to be a parabola. And then this last one, you might hear it called an exponential curve. Sometimes that's a name we'll give to something like this. So a parabola, that looks like that kind of U-shaped. You're going to have that. So this is any old parabola. That's the general shape that you'll see. Exponential curve, it's going to be values above the x-axis here. Notice I'm not drawing in the x-axis and y-axis. I haven't done that with the rest of these because hopefully you can make that assumption here. Hopefully you're all right with that. Sometimes I feel like it's important, but right now with just quick sketches, I don't feel like we need to do that here. And so I think that does it for that. And so now let's check out an example. There was one other thing I wanted to write though before moving on. There, where did that go? So before we move on, underneath this, let's make a little note on your paper. Just put this underneath your stuff here. But for help with, I'm trying to make this video as succinct as I can, and we've done a lot of the linear function stuff already. So I'm not going to have you do that again. We're not going to do that again here. So for help with linear functions, you can see example 2 and example 3 on pages 363 to 364, or refer back to your 6.7 notes. That's when we talked about linear functions, linear equations, and graph those things. So, or refer back to your 6.7 notes. So please make that note on your notes underneath this part, and then we can move on to example 2. So we're going to talk more in depth about quadratic and exponential. I feel like we've hit linear pretty hard already. So check out the book if you need a little extra help with that. You'll notice here the path of trajectories is going to be in a parabola. If you hit a golf ball, it's going to go in the general shape of a parabola here. If you're shooting a basketball, it's going to go in that general shape of parabola. Gravity will affect it. in a parabolic way. So example 2, those are just some real life applications to parabolas and where they get used. Physics used a lot because of gravity. We're going to consider the equation y equals negative 3x squared plus 6x minus 2. And we're going to have a few parts to this one. So this is going to be part A. Let's determine first. And I'm kind of putting a lot of different problems they have as separate examples all together in the same one here, so we can consolidate and still hopefully understand everything that we need to understand in this lesson. So determine first if the graph opens up or down. So first of all, we have to determine if it's in that general form. Is it in the y equals ax squared plus bx plus c form? Look at that, and yep, sure is. We've got this as my a value though, so let's put that in a different color. Negative 3. My b value is positive 6. My c value is 2. So is the graph going up or down? That all depends on the a value. If you got it in this form, just look at the a value to determine that. So our solution here, look at the a value. Since a is negative, let's underline those two things. A is negative, it's going to open down. The graph opens down. If it was positive, it would open up. So let's write that as an extra note under there. If A is positive, it will open up. Right. Part B. Determine the axis of symmetry. Think of it as an axis kind of as a balancing point or a balancing line. Axis of symmetry would be a line that it's symmetric about, so it looks the same on both sides of the line. So an axis of symmetry of the parabola. We know it's a parabola because it's in this quadratic form. And this is the equation you're going to use always to determine the axis of symmetry. X equals negative b over 2a. That might ring a bell from algebra or algebra 2 if you've taken that already. But let's circle these two things, connect those. That's what we're always going to use for axis of symmetry. So that is the equation we use. And so let's do our little triangle. That means therefore. So we have therefore x equals, let's plug in our values. We've got negative, and then b is 6, so I'm going to plug in a 6. I'll use parentheses for the things I'm plugging in. And then 2a is 2 times negative 3 on the bottom. That becomes negative 6 over negative 6, which equals positive 1. And that implies that x equals 1. That equation, that line, is the axis of symmetry. So that is my answer. If I'm going to graph that, which I will get to in a little bit, we'll get there. I know you're just dying to graph it, so just hold on. We'll get there. But we will use that line, x equals 1, for the axis of symmetry. Now, part C, determine the vertex of the parabola. Well, if we know it's symmetric about this point, don't draw this off to the side. This is just a visual to help you think about what I'm talking about here. So we're going to draw a better graph later, but this is just to help us think. So here's axis of symmetry, x equals 1. We know that the vertex is going to lie somewhere on there because it has to be symmetric about that line. So maybe it's like, we know it opens down, so I can eliminate what I was just about to do there. It's got to open this way instead. So it's maybe it could be here, maybe it would be here. I don't know yet, but it's got to open down, and that's got to be the highest point right there where x equals 1. That's the vertex of the parabola, the highest or lowest point. If it's opening this way, then it would be the lowest point instead of the highest point, but the vertex is either the highest point or lowest point, depending on how it's opening, up or down. So let's figure that out. Well, I know that the x value right here from the axis of symmetry has to be the x value of the vertex. And so that's part of what I'll say here to start. So the x value of the vertex will always be the value from the axis of symmetry equation. So let's say therefore, to find the y value of the vertex, we'll use this. So we're going to go back to the general form up here. We're going to plug in x as 1 and figure out what y equals at that point. So maybe it's down here in the negative portion, maybe it's up here in the positive portion, maybe it's right on 0 for the y value. Let's find out. So I'm continuing this example here. We've got y equals, I'm just rewriting the equation as it was initially, and then I'm going to plug in 1 for my x value. I got y equals negative 3 times 1 squared plus 6 times 1 minus 2. That becomes y equals, this will be negative 3 times 1 would just be negative 3. I'm going to have plus 6 right here, minus 2. Therefore, my y value is going to be, put these together, negative 3 plus 6 is 3. 3 minus 2 is 1. Look at that, happen to be the same value. So, interesting. So y is equal to 1. Therefore, this is going to imply that the vertex is at 1, 1. Beautiful. All right. So let's move on to part D now. We are now going to determine the y-intercept. And a little quick note to make here that I feel important to note. There will always, let me insert that in there. There always will be just 1. So there's only one y-intercept. So think about that here with our graphs. It's only going to cross a y-axis in one point. This one would eventually cross way up here, so this one way up here, but it's going to cross the y-axis somewhere, but just at one point if it's a function, if it's in this form. So it'll always just be 1. And x-intercepts, and with x-intercepts you could have, here you would have 2. If this would keep going, you'd have an intersection there and there. Same thing here and here. But you could have none like this one, or you could have a graph that just touches right there. Maybe it just touches at that point, or maybe it just touches right there at that point. Then you would just have one solution. So it could be 0, 1, or 2. So there will be 0, 1, or 2 of the graph. And so let's figure out the y-intercept. It's going to be a lot less work for that than the x-intercepts. So the y-intercept first, let's start with that. We'll put the x-intercept over here. Just like before, we learned in a previous lesson recently, this is where the x value equals 0. The y-intercept is where the x value equals 0. So we're going to take that and we're going to plug in negative 3 times 0 squared. This is just this equation right here, plus 6 times 0 minus 2. Simplify that. This will cancel right here. Let's do that in red, or whatever color you're using, because that will be 0 times whatever is still 0. 0 times 6 is 0. You're just left with negative 2. Therefore, you have y equals negative 2 is the y-intercept of this graph. Notice that's different than the vertex. The vertex is just the highest point it's getting at, and then the y-intercept is where it's going to cross the y-axis. So back to this graph here. If it's at 1, 1, maybe that's like this one, and it's going to cross the y-axis at negative 2. So down here, something like that, our graph starting to get an idea of what it's going to look like, seeming like that one is what it's going to be like. We'll draw that more carefully in a bit. But this y-intercept, this is the y-intercept right here. Y equals negative 2. And for the x-intercept, this is where y equals 0. Where it crosses the x-axis is where y equals 0. So we're going to take that value and we're going to say that 0 now equals negative 3x squared plus 6x minus 2. We're solving this. This is the general equation to start, but I plugged in 0 for y. And with this, yes, you could try to factor it. This one actually wouldn't factor. So when all else fails, what do? We use the quadratic formula. So we're going to plug in x equals negative b. Oh yeah, the song's back. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Hey, that's not bad. Should be doing a choir. Yeah, right. So we're saying with this is in the quadratic equation or the quadratic formula form that we need. So we're going to use, with that, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. There it is. All right, so we're using that. That's where that came from. That's where that mess came from. All right, so we have negative 6 plus or minus the square root of 36. This will be negative, negative, negative. We'll make a negative. 3 times 4 is 12 times 2, 24. And so from there, we've got that over negative 6. I'm going to continue this thought up here. You can just keep going with yours. I'm just running out of space. So this would be the square root of 12. We'd have that over negative 6. This I can rewrite as taking the biggest perfect square that goes into 12. That would be 4. And then I'm going to take that out. The square root of 4 is going to equal, so I'm continuing down here now. That would be 2. So the 2 comes out. 3 is still in there. I have that over negative 6. I could reduce this. Let's do that in a different color now. This would become, you could reduce each one by 2 here. So this would be a 3. This would be a 1. This would be a 3. And so we'd have, you could write it like this, negative 3 plus or minus square root of 3 over negative 3. But the negatives could cancel, and then the plus or minus would become minus or plus, which would still be plus or minus. And so you could write that more in a positive way. You could have 3 plus or minus radical 3 over 3. That is going to be your exact answers. These are approximately, these values are approximately 1.577. I just decided to go with 3 decimal places for this, just because I could, because I made up the directions for this one. So read the directions carefully, do what it says. So these are your x-intercepts. These are your values where it's going to cross that x-axis. From there, we'll need to continue this problem. We're doing part E now. Now we're going to sketch the graph. So let's do that here now. Sketch the graph of the parabola. And I want to draw this to scale now, so I'm going to draw a more careful graph. So get out a ruler or something like that. Make your scale nice. Make sure everything is the same in each direction. I knew my x-intercept was negative 2, and I knew my graph was going to cross, or the vertex was at 1, 1, and it opened down. Therefore, I'm going to draw my graph kind of like this. I don't need much in the positive direction for y values, because it only gets as high as 1, 1. That is the highest point it gets at. So right here, let's draw that. We've got a point at 1, 1. This is the vertex of that parabola. And let's draw our axis of symmetry. You'll generally see it drawn, I think at least books I've seen in the past. They might use a different colored line or a dashed line, so let's do that here with a dashed line. This right here was the axis of symmetry. This is x equals 1. That's that value. Let's label our axes as well here. So this is going to be x, this is going to be y. This right here is the vertex. Let's also label that. So this, we already figured this out from before. The vertex was at 1, 1. So I don't think I'm just making this stuff up. We already did this. We did this here. We got the vertex here. We got the axis of symmetry right here. X equals 1. And we know the intercepts for the y-intercept, that was at -2. So that we are going down. There we go. There's y equals -2, or there's the y-intercept at 0, -2. Let's label that. Use our different color for that. So this is the y-intercept. This is at 0, -2. And it's going to cross the x-axis, and we can kind of see the general shape here. It's going to be symmetric about that, so we're going to have another point right here. That's easy to draw. Easy to draw in there, and we know it opens down because that a value is less than 0. So the general form is right here, but let's just verify that those points make sense based on our x-intercepts. So 1.577 and 0.423. Let's draw those points in here. So it's a little less than halfway here and a little more than halfway here, and that seems to make very good sense. So right here, it's just going to keep going that way, and it's going to open down because of that a value, and make it symmetric as best you can. Let's label these 2 points right here and right here. These were the x-intercepts. You had 0.423, 0, and you had 1.577, So there's our graph. There's a sketch of our graph. One more thing to do with this one. I know this is an involved problem, but I'm trying to combine what the book sometimes, or what the book has separated into several examples. I'm trying to put that all together here. So determine the domain and range of the function. Domain and range of the function. Some more things in a different color here. Domain, all possible x values is what that is. So what is possible to plug in for x? The range, this is all possible y values. And so let's look at our graph. That's the easiest way to determine that. The domain, what can you plug in for x? And you can also think back to the equation. Is there anything here that you could not plug in? Is there anything that would say, oh, you got a no solution, or this doesn't work, you can't take the square root of a negative, stuff like that. You're dividing by 0, stuff like that wouldn't be able to be possible. But here, I could put in negative values. Oops, moving too fast there. We're moving ahead. Wrong button. So I could plug in negatives, I could plug in 0, I could plug in positives, I could plug anything I wanted into there, and I would get an output value for y. So this one would be all real numbers. If you want to use a capital R with a second line like that, you can also write it like that. So all real numbers, or you can say capital R like that. This works, or this is the answer, because any value for x works. And the range, this one, it's not all real numbers. What's the highest y gets? Well, y would be anything negative would work. Anything negative would be a possibility. But as you move up, you get up to 1, and then there's no more points after that. There's nothing up here. So no y values will be greater than 1. So the way we can write that in our set notation that we learned earlier in the year, we have y such that y is less than or equal to. It could equal 1, could be right there at 1, but it can't be anything higher than that. So y is less than or equal to -1. The vertex is always the highest, or if it was opening up, it would be the lowest. So I'll put highest / lowest y value. Okay, so that's it for that one. We've got one more. You've seen this one. Example 2, though, definitely a long example, multiple parts to do, but hopefully you found it helpful, and hopefully it was a good review if you've seen that sort of stuff before of quadratics and how to graph those. So for help with the plug and chug, I'm going to call it plug and chug exponential problems. You should check out, you should see examples 8 and 9 on page 369. I'll put it's not factorial, okay? Yeah, it's not 369 times 368. That's just emphasizing that I want you to look there. So rather than do more examples, I think those ones are pretty easy to just look at and be like, okay, I got that. I understand. I understand what you're driving at, Mr. Wagner. I understand where we're going with this. Yep, so determine graph y equals 3 to the x power first, and determine the domain and range. I promise this one will be much shorter than the previous one. So determine the domain and range of the function. So let's graph it first, and with exponential equations, with this one at least, we're not going to go very far negatively with y values, so I'm going to do something like that there. I'm just going to go 2 down that direction. Let's draw our arrows at the end of each part there. Hey, there you go. That's our x-axis, our y-axis. And on this one, I'm going to go up. I'm going to say each 2. Is that going to be enough? No, I'll go with 1. No. There we go. Each value here is going to be worth 5, or each one as I move up is worth 5. So 5, 10, 15. Keep that scale the same. 20, 25, 30, 35, and so on. This will continue. But in this direction, since this scale is different, I just want to make sure that we know that this scale is still going to remain just 1 at a time. So we'll go up that way. This will be 0, -1, -2. So if you're ever changing your scale for my class, my students, we need to show that what scale has changed, which one has stayed the same, or maybe they both changed. It just kind of depends on how we're going to fit that into here best. And so here, let's make an xy table, or an f of x table. You can call it that too with functions. F of x, again, is just another way to write y. It's just a function notation. And let's find it for all these values, all the way up from -3 to +3. So if you plug in -3, I'm going to say with this one, we'll need to do a little preliminary work. That's 3 to the -3, which is the same thing as 1 over 3 to the +3. This is like this over 1. We'll put that in red here. It's the same thing. That over 1 is the same thing. If you have negative powers, they switch places in the fractions, remember. Excuse me. So here we'll have 1 over 27. In a similar way, 3 to the -2 would equal 1 over 3 to the +2, which is 1 over 9. And then 3 to the -1 would equal 1 over 3 to the +1, which is 1/3. 3 to the 0, anything to the 0 power is always 1. That's just something that we have to memorize. It's kind of based on limiting ideas, and as things approach that, that's the value that makes sense to fill in, not 0. That's the most common mistake there. So anything to the 0 power except 0 to the 0 power is just 1. 0 to the 0 power is just crazy. That's what that is. And then this would be, I'm sorry, I'm getting ahead of myself. That would be 9. Oh, entertaining myself here with crazy voices. I'm not very good at doing Yoda, but that's kind of how he sounds to me. So these are my x values right here. Let's circle those, and these are my corresponding y values. And to make the graph, let's just plot those points. So at -3, you're going to be really, really, really close to 0, almost right on the line. Same thing with -2 and -1, extremely close to 0. 0 is going to be at 1, so it's going to cross still very close to 0 there. And then 1, it seems like, man, this is not growing very fast, this is not very interesting, but all of a sudden, exponential equations, they just start to rise like crazy. And you'll see some of the pictures I've got drawn over here, not drawn, but depicted over here. I did not, yeah, I drew that picture of those rabbits and those people in Bangladesh, in the most populous, the most densely populated country in the world, Bangladesh. This is, I think, the capital city, Dhaka. Population, that is represented very often with exponential functions or exponential graphs, because population is related in an exponential way. Same thing, you could think of things breeding like rabbits or rabbits. Maybe you've heard of that before, like rabbits. No, like rabbits. Rabbits just breed and proliferate like crazy. So does bacteria. Another thing you can represent exponentially is money. The growth of money is often related in an exponential way. So when we're talking about interest, definitely talking about exponential growth there. So the domain, what x values can you plug in? Well, I could go as far back negative as I wanted to. I can use 0. I can do anything positive. So this becomes, or this is, all real numbers for the domain. And the range, it looks like my y values are always going to be greater than 0. I'm going to get insanely, that's it, like extremely and insanely at the same time. I'm going to get insanely, extremely, extremely close. I can't, what am I saying? I'm going to get really close to the line right here, y equals 0, but it actually will never touch it, and so you also will never get negative with this function. You have y such that y is greater than, not or equal to this time, because it can't actually equal 0. So just y so that y is greater than 0. Let's make one final note. Yes, we're just about done. So one final note about this here. So this is not or equal to, because it will never actually hit 0 right there. And so writing over the money, that's like, that is treason. That's not treason, but that is against the law, I think, to deface or destroy money. Not a good thing. A good thing that's not real. Yeah, I'm done. That's all. That's all I got here. Hopefully you found that helpful. A good review if you've seen stuff like that before. If you've never seen stuff like that before, hopefully it gave you a good idea of what to expect with things like this. Hope you have a good day, and I'll catch you later.